All right, and I think we're going to do 9.5, probably I think together with 9.6, it looks like, based on the sections. Yes, 9.5, 9. We're going to do 9.5 through 9.7 all as one section. Yeah. All right. So 9.5 through 9.7. That's what we're going to be focusing on. All right, so 9.5 through 9.7. This is where we finally get the conservation of momentum. But we talk about conservation in the sense of it's always going to happen with momentum, but not always going to happen with energy. Do you remember from last year when we had two types of collisions? Yeah, elastic and inelastic. So let's start by saying that momentum initially is always equal to momentum at the end. This is always true. Always, 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 always. Okay, so momentum is a constant. P initial equals P final. But energy loss or energy change is not always going to be the same. So we have those two scenarios, elastic and inelastic. Here's how I remember them, because when I was your age, honestly, I would confuse the two. And if you confuse the two, it's a really big issue, right? Because you're using the two wrong things. Elastic. Things that are elastic. Things that are elastic. I think of things like things that bounce off of one another very easily. Like a bouncy ball, a pool ball. Something that rebounds off of something else. Because I think of elasticity, coefficient of restitution is the amount of the energy that is bouncing back up off the ground. So for elastic, think of bouncing off objects. For inelastic, think of it being embedded in the other object. Okay, like the ballistic pendulum problem, which is what you guys are actually focusing on right now for Science Club, which we're going to focus on here. We're going to talk about that. But elastic is where they hit each other and separate afterward. The best example of elastic collisions, not the best, but one of the best, is pool. Actually playing pool. Now, there's a lot that goes into pool. The ball rotates. There's more than just this. But the concept of those collisions, it's pretty close to elastic. It's not perfectly elastic. It's in between these two.
It's not like the Newton's cradle.
Yeah, very much like Newton's cradle. Yeah, that's another great example. Newton's cradle is very close to being elastic, which is why what?
It goes through.
For a while, right? Eventually, though.
It like slows down.
Yeah, because it is partly inelastic. Those marbles are losing energy at a very, very, very low speed or a very low rate, the energy loss. Where is the energy loss in Newton's cradle? Sound.
As it transfers between the marbles, right?
Careful with that. I need more of a clear statement.
Air resistance.
Air resistance, sound.
Heat. Like that's
Heat.
like the friction between each ball when they move.
Okay, so friction or deformation. I know there's very minimal deformation, but there is still deformation of each collision occurring. And that's kind of what you were talking about, the transfer there. When you say transfer,
Yeah.
transfer means keeping momentum, So
Yeah.
be careful with that phrase. So there's definitely air resistance, there's definitely sound, there's definitely deformation in the ball, there's some frictional loss when it hits. One other spot where we lose energy in Newton's cradle.
Like tension.
Yeah, the rope itself. The rope itself. Okay, so the tension in the rope means that there's going to be a pulling force on the eye hook. If you want to look up there, you can see the eye hook up there. And the rope connected to the eye hook as it swings creates friction. We were talking about it today. Chris and I were talking about this for a ballistic pendulum, and he said maybe we'll use bearings at the top so that as this thing moves back and forth, there's very little friction. Okay, to reduce the amount of frictional loss. But those are the areas you'll lose it in Newton's cradle. In general, though, in elastic collisions, you account for the loss in energy. Elastic, we don't account for the loss. So for elastic, if we don't account for loss, we could say that this equals this. But for inelastic, we would say this does not equal this. For all inelastic processes, it's a loss in energy. So we could write that as the following. We could either write, if we want to, K0 equals K plus the work done by friction in absolute value terms. Even if it's negative, we're going to consider that to be a positive value here because we're adding it on to what we have at the end. Or we could say this. where this is assumed to be a negative quantity. I don't like to move it over. I don't like to write this as a negative. I like to write it the way it's written here and saying that you have kinetic energy plus a negative amount of energy giving you what you have at the end, which is lower energy because you've lost energy. Or you say you started with a lot of energy, you end with less, and how much is missing is what's over here. Okay, that's why I'm putting absolute value over here by work done by friction, whereas here I'm leaving it as work done by friction because that would be a negative quantity. But I need absolute value to make it positive on the right side, obviously here. But that's the general concept that we're going to look at for the next sections, 9.5, 9.6, and 9.7. This is literally summarizing all three sections here. They kind of take you one step at a time. Okay? So let's do a couple example problems so we can see this kind of at play. The first example problem is a pretty simple one. Okay, so let's start with that. And the example problem says the following. And we don't have to do the exact wording of it, but here's the scenario. You've got an object. It's moving forward. Then suddenly there's some separation. Okay? So the object's moving forward, moving forward, moving forward, and then something is fired in the reverse direction from that object. Something's fired in the reverse direction. Or something's fired in the same direction, either way. What can we conclude from something like this? Let's say this velocity here was something like 10. We can automatically recognize that this velocity, what do you got, Chris? Greater than 10. And I should maybe draw my vectors accordingly then, right? Maybe make this guy nice and long so we can see that better. I'm not even drawing forces, just velocity. Why is it greater than 10? Why must it be greater than 10, Chip?
Well, I mean, if you're firing in the opposite direction of something off of it, you're like putting a greater normal force on it, and thus it has to accelerate it in that direction, and therefore like the velocity has to be greater.
Not normal force, but yes. Everything else you said sounds great. It's recoil, right? You know recoil? If you've ever fired a gun, or if you've ever fired something at all, or even if you've ever I'm trying to think of another example. Even throwing something, like you take a baseball, like really throw it, you feel your body kind of like kick back a little bit, and the torque that you're providing when you throw it, it actually kind of helps the ball go forward by you pulling back. So the concept is this: it's got some momentum to start, right? Whatever the momentum is. Let's say that the mass of this is 20. So we have a momentum of the system of 200 to start. And then after the explosion, we have to consider what's happening. Okay? Well now, let's say that this becomes 19. And let's say this is 1 then, obviously. Let's say the velocity going back for the projectile with a mass of 1 is 5. And our question is, what is this v, right? We know it's greater than 10, but let's say, what is the velocity of the object now? And the key is to recognize that if it's propelling it backward, what kind of a velocity momentum is that? It's propelling that little object backward. So what kind of a velocity is it? What do you think? What do you think? It's backward, Chris?
Yeah.
You had your hand up, sorry. Was that a hand up or no? You're just stretching.
Yeah.
Oh yeah, so if it's propelling backward, what kind of a velocity must it be? A negative velocity. That's the whole key to this problem. Vectors matter for linear momentum. Remember energy? Last chapter? Did direction matter much with energy? Energy is a scalar quantity. Kinetic energy, potential energy. Potential energy stored in a spring, 1/2 kx squared. We never had a negative value because of direction of energy. All we accounted for was negative as in like a loss of energy, right? But not directional. Here, direction matters. So the momentum of this object is going to be mv, and we'll say this is like m1v1 plus m2v2. But in the beginning, we just had mv. But now it splits into two parts. Right? We did 20 times 10 earlier to get 200. Now we've got to do, for this one, the mass of the little thing projecting backward is 1. Its velocity is -5. The mass of the second part is 19. And we're trying to find out its velocity, v2. But the key is that we know what this will sum up to because we had the momentum in the beginning of the problem. Pat, what was that momentum in the beginning of the problem? 200. So you know what? That means that this quantity has to be equal to 200. The momentum initially equals the momentum at the end. So therefore, this V2 has to be greater than 10. It's not going to work if it's not. What do we get for V2 in the end? If we add 5 and then divide by 19, right? That's what we would be doing. We'd be adding 5 and then dividing by 19. What's 205 divided by 19 going to give us? 10.8? Is that what it is? Okay. Again, we're setting this equal to 200. This is equal to 200. And again, it's because the initial momentum equals the final momentum. Conservation of momentum at the top. All right, here's a question for you. Follow-up question. Is this elastic or inelastic? Give mathematical evidence.
Elastic because initial momentum equals final momentum.
What do you think? You all agree with her? I don't. Careful. That's if initial energy equals final energy that it's elastic, right? It's energy that tells us elastic versus inelastic. You thought of momentum, be careful. So what I'm saying is, you can't really tell unless you calculate. We don't know if this is considered inelastic now. I can tell you now that it's going to be inelastic. Because usually explosions or collisions where things stick together, those are inelastic. Because it must take energy for those things to deform. The shape is deforming. So it's going to be inelastic, but we want to prove it. So let's find the kinetic energy of the object in the beginning. What do we got? 1/2 mv squared in the very beginning. What do we get for kinetic energy? 1/2 times 10 times 20 times 10 squared. 1,000. 1,000. It's all right. Is that, are we all in agreement with that? We checked our numbers, right? 1,000 in the beginning? Okay, now give me the kinetic energy at the end. We have 2 objects now, though. 2 objects at the end. So we've got to look at the kinetic energy afterward and say, okay, 1/2 m, m is 1, v squared. Remember, for energy, the negative doesn't matter because we're squaring it. Plus 1/2 m times v squared. What are we going to get for our energy comparison here? So we've got 1,000 up top, and then what are we going to get down below here? 2 objects, both moving, both have energy. We have to sum their energies together to see how much energy is in the system afterward. Chip's the calculator guy today? All right, it's fine. Go ahead, Chip.
1,176.2.
Yikes. Correct? Incorrect? Correct? Incorrect? I'm trusting you right now, but I'm just asking for verification, right? Thanks, I'm not trusting you.
I'm gonna say it's correct. I'm gonna advocate for myself because the work that's gonna be done by friction or whatever it is gonna be the absolute value. Should be greater than the initial.
What did you get?
1120.
Yeah, I got 1120.
What'd you get?
1120.
1120? 1120? Still greater though, right? That's what we're noticing. So what's the deal here? What's happening? How is it possible that we have more energy afterward? How is that possible? Chris? when we round it up.
velocity.
What do you mean? I don't think it creates that much of an issue. 1120, right? That's the number we're talking about? That's a huge difference. I don't know. You're talking about the 10.8, Chris, right?
Yeah.
And what was it? It was like 10.77 or something, probably?
Yeah.
It's probably not that, but I like the idea. What do you think? How could we have more energy afterwards? What's that? So what kind of energy did the system have in the beginning that we didn't account for? Yeah, it's got some sort of chemical potential energy. We're not going to get into chemical energy, but the idea of it is that for an explosion to occur, you're going to have some sort of energy stored in the bomb. We use the phrase bomb for now, right? Okay, you have something stored in the apparatus that causes it to explode. So in this case, there must be some sort of chemical energy that was in the beginning of the problem to cause a difference in the kinetic energy from the beginning to the end. Now, what if we had a lower value in kinetic energy afterward? What if this number were lower? Forget the scenario, which is in general. What if there was a collision or an explosion or something happens and there was a lower number? What can we conclude? What could the reasoning for that be? If it were lower as a number. If it were lower. What do you think? Check that.
Like things collide and stick together and they like continue moving.
Mm-hmm.
Or maybe they're moving like opposite direction, but in the same direction. I mean,
And what would cause that loss in energy specifically? What would cause? You're right. What would cause the loss in energy? If they stick together, what causes it?
that difference in velocity, I'd say. So
Conceptually, not mathematically. Conceptually, what causes a loss in energy if two things stick together?
deformation.
Yeah, deformation, fusion, heat. Have you ever seen a car accident where the bumpers stick together afterward? Or the front end of a car kind of gets wedged into the back end of another car like that? A lot of rear end accidents that happens, and the bumpers will physically fuse together. There's such a high impact of velocity that there's enough heat generated that they'll actually fuse, like welding, fuse together. And that'll cause a lower energy afterward than the energy it had to start. The key here is this again. A difference in KE means inelastic. It means energy must have been lost or used up somewhere along the way. There must have been some sort of energy change occurring here. Form of energy. It's not just kinetic anymore for inelastic. When it's elastic collisions, the kinetic in the beginning will equal the kinetic at the end, and you'll say that there's no loss or gain in kinetic energy because the system was an isolated system, if I use the phrase, isolated. Okay. All right, there are a couple equations your book writes down, and these would be useful ones to have in your calculator. They're not on your formula sheet, so I'm going to jot them down for you. Okay, and this is on page 237 to 238. This is for elastic collisions. For elastic collisions. Let me just make sure I'm right with this phrase. All right. So this is the general, let's just say elastic with object 1 attacking object 2. So diagram wise, okay, this is what we're looking at. Object 1 is attacking object 2. Object 1 hits object 2, causing object 2 to move forward, and then object 1 either continues with it or gets rebounded. That's why I put question mark there. It could go either way. Object 1 might hit the first object, and if object 1 is big enough, it'll keep going after it hits the first object. But if object 1 is really small, it'll rebound off. Think about like a 3-year-old running into a parent, right? Ever see like a little kid literally just run to an adult? Sometimes they'll run into them and just boom, bounce right off them. Because they're literally like a wall compared to a kid. So a really small object attacking will get rebounded off. But a large object will continue forward. Now, if it's exactly the right size, what will happen is, here's what happens, ready? It's pool. You hit the cue ball hits the other one starts to move, and the cue ball just stops. It's rare that happens, right? You hit low on the cue ball, the ball comes back, you're drawing it back, we call that English, you spin on the ball. If you hit higher on the cue ball, it puts a little front spin, so when it hits the ball, it'll continue afterward. But if it's going toward a pocket, you don't want it to continue afterward. When the ball just collides, and then the other one moves, and this one stops, that's the in-between. So there's 3 scenarios. The little ball could either get rebounded off, or it could be a bigger ball and continue following, or it could be exactly the right size, hit the second one, and just stop there. Okay? And again, this is elastic collisions we're talking about. So here's the equations. So V1, they're calling it F for final. The velocity of the first object after the collision, the generic solution for it, is m1 minus m2 over m1 plus m2, all times the initial velocity of object 1. And this is combining conservation of momentum and conservation of energy. I'm using both concepts to make this true. And then the second object's velocity after the collision is given as 2m1 over m1 plus m2 times, again, v1 initial. So these 2 formulas can be really useful for an elastic collision on a multiple choice problem. You don't want to have to derive them and go through the process. What I'm really doing here, or what the book is doing, and I'm showing you here, is they're combining these 2 equations up top. Here's the 2 equations. So they're combining conservation of momentum, which is written up the top there, with conservation of kinetic energy. So those 2 equations written at the very top, with a lot of algebra and substitution method a couple times here, you get to these 2 solutions down here generically. We're literally solving for V1F and V2F, but it's in a couple spots, so it's just going to take a little bit of work. Okay? Again, this happens on pages 237 to 238. They don't even show the substitution really here. They kind of show it at the end. They say, after dividing and with some more algebra, we get to this solution. It's not a difficult thing to get to, but it'll take us 10-15 minutes just to derive it. There's no point in going through the derivation because it's not something that you're going to want to have to derive on a test anyway. So I would recommend having this scenario as one of those scenarios in your calculator. So when you get to a problem in multiple choice and it's an object or it's an instance where one object is attacking the other, think about which scenario or which case you're looking for here. They give 3 outcomes for this.
So it says, does
Yeah.
that equation go to the first scenario?
So this is the velocity of the first object after the collision. This is the velocity of the second object after the collision. Yep. And Kara, based on the masses, we don't know whether to move left, right, or stay still. And those are the 3 scenarios I talked about. And your book outlines all 3 scenarios. They talk about if the objects had equal masses, completely identical masses, like the same ball, billiards, pool, the initial ball will stop. So let's go through the 3 scenarios now. I'll put them up one at a time. Okay? So scenario 1, let me move this over a little bit so I can see on the screen. Scenario 1, come on. If M1 is equal to M2, then the first ball will stop, and the second ball will take on the velocity the first ball had. Again, if the masses are the same, and think about it logically, right? Look at the equations, people. What's m1 minus m2 if they're the same mass? What is this going to become? 0. So 0 times anything is 0. How about over here? Take a look over here. If the masses are the same, double m1, well, this would be m1 plus m1, right? If they're the same. So I got double m1 over double m1. Those cancel. I'm left with v1, 0 for this one. Okay, so when the masses are the same, these are the two results we get from those equations. If the, let's see, if the attacking body is greater, let's see, then V1F is still going to be going in the same direction. How do I do that? Let's say it follows or trails. V1F trails object 2. V2F is approximately double the initial velocity. Let's put an approximation symbol there. Approximately. Okay, V1F trails object 2. In the third scenario, if the first object is less than the second object, then V1F rebounds off of object 2, and V2F, this is an interesting one. This comes out to be, this is probably not one you're going to have to even write down or memorize, but just so you know what it is, times, that's what it comes out to be. And this is an approximation again here. Okay, approximation. The book then specifies another, give me like 10 more seconds here. The book then says a little bit more. It says, like, if the masses are much, much different. How do you write much, much different or much, much greater? Not just greater than. What's the much greater than symbol? Anyone know? Math, the book uses it. Uses a calc now? A double symbol? So greater than symbol twice means that mass 1 is far greater than mass 2? I know, it's kind of ridiculous, because what is far greater, right? It's all relative. But if mass 1 is much, much greater than mass 2, then although it's going to trail the second object, it's not going to lose much velocity at all. It's going to pretty much maintain the same velocity it had. If the second object is much, much greater than the first object, it's going to rebound with pretty much the same velocity it had in the negative direction. Okay, but the idea is that it's going to rebound or it's going to trail. That's the key to these problems. Over the weekend, I think I gave you guys some homework, right? I think I gave you homework in 9.4, 9.3 to look at. Okay, so catch up on 9.3, 9.4. This is 9.5, 9.6, 9.7, and I'll give you an assignment for that. I'll add that to the regular assignment and to the problem set. Okay, you have problem set questions up already. I will also try to start sending you out a couple of different problems of free response to practice. The free response are very much not going to be just momentum though. This is where we start getting into a lot of problems that are combined, where energy transfers to momentum, and then the momentum transfers to kinematics, and you have to find the range of the object. So the free response, you're going to be putting together all of the topics you've learned this year into these free response coming up. So I'll start with that maybe next week. I'll give you the free response. But over the weekend, get yourself a good head start on 9.3, 9.4, and if you have time, I'll start putting up 9.5, 6, and 7 for you to work on. All right, so let's look at an example. The example I want to start with first, we'll be looking at for this one, and it's conservation of momentum. So here's what the problem says. I'll read it while Matt's writing this down. So it says, a firecracker placed is on page 232. This is an example of conservation of momentum with a two-dimensional setup. A two-dimensional setup, not a one-dimensional.
Just go back to that side.
Yeah. Again, it's a two-dimensional setup that we're a firecracker placed inside of a coconut. Just think about that, right? Okay. Now you can go.
Why is this
Exactly. For physics, that's why.
Wait,
For the love of science, we do these things, I guess. What is that?
A physics textbook with that.
A physics textbook.
Oh, God.
Oh, you've seen the other ones. What was it, a sardine can at the time? No.
Yeah, the hood, remember the hood?
The hood one, there was a rock.
There was a sardine can at one point, remember?
Yeah,
Yes, there was.
A can of sardines. What
The
was that?
raccoon that ate trash food.
Oh, that's right, the raccoon too.
So what happens when you let scientists...
When physics teachers need to write new editions of textbooks, and this is what, the 10th edition, that's what happens pretty much. They run out of problems to make unique, so they start
Or
writing
there was
firecrackers
the
and
bike,
coconuts.
the human powered vehicle.
So, a firecracker placed inside a coconut, aka
Bomb.
a bomb, explosion, grenade, whatever you want to use, right? So think about on the test, they do bomb this idea. Initially at rest on a frictionless floor, blows the coconut into 3 pieces that slide across the floor. Somehow they don't rise up in the air, they only slide in a 2-dimensional plane. An overhead view is given in the diagram. I'll draw that overhead view in a moment. Piece C, the 3rd piece, I guess, with mass 0.3 m, 0.3 of the original mass of the coconut, has a given speed of 5 meters per second. What is the speed of the second piece, piece B, with mass 0.2 m? With mass 0.2 m. So we need the diagram because we're given about a bunch of geometry in the diagram that has to be used here. So let's start with the diagram first. So here's the coconut to start. And then after the explosion has occurred, the coconut has 3 pieces. These are the 3 pieces of the coconut. The one on the top left is called A. The one on the top right is called C. The one on the bottom is called B. The angles are given as follows. B is like this. Its direction of motion. C's direction of motion is like this. A's is like this. And we're told that this angle is 100 degrees here. We're told that this angle here is 130 degrees. And obviously we can get the other angle as a result. The mass of part C is 0.3, the original mass. This is the original mass over here. The mass of part B is what we're looking for. No, sorry, we're looking for the speed of part B. The mass of part B is 0.2, the original mass. The speed of part C is 5. And that is what we're given, okay? So let's go through this problem. And our goal again is to find the velocity of part B after the explosion. I don't need to use the F. I'm using it because the text used the F there. But without the F, I can just write VB or VC indicating that it's not the initial velocity because that was 0 right here, right? This is the before and this is the after. I remember before and after. Before, nothing is moving. So if nothing is moving beforehand, what is the total momentum of the system beforehand? So what must the total momentum of the system be afterward? Because of conservation of momentum. So we know already that if we add together these 3 momenta from A, B, and C after the explosion, it's got to sum to be 0. In how many directions? How many directions? In the X and the Y direction, both. So we have to look at our momenta independently. So let's take a look at the X direction like we did last time, and then the Y direction. And again, we have a before and after, but I don't need to write the before here. Again, I don't need to write the before because of the fact that I know before is 0. So I'm not going to write a whole equation here for before like I did last time, and then after, I'm just going to go right into the after in the X direction. Now, the angles may look confusing at first, right? The angles can look a little bit confusing because if you look at the system, you're like, all right, well, how much of angle, or how much of part C is in the X and the Y based on these angles of 130, right? That's a little bit confusing there. So what might we want to do in a problem like this? Think about inclined planes to help you. I don't even think your book suggests this, but I would suggest it for sure.
Break it up into
X and Y components for sure.
You make your own X and Y.
We make our own XY axis. And what might we do like on an inclined plane with our axis? Instead of being like this, what are we going to physically do with them? Rotate. Tilt. Good. Tilt, rotate. Rotate them. Let's tilt or rotate them in such a way that it causes one of our pieces to only move in the X or only move in the Y. follow what I'm getting at? Why am I saying that? Who can explain why I'm specifically choosing an XY axis system so that it only moves in the X or Y for one of the pieces? Matt?
Because that zeroes out the other, the y value.
It zeroes out the other component. Very good. If it's the X that was going, then it zeroes out the Y. If it's only along the Y, it zeroes out the X. Chris?
If that's 180 degrees and 130 degrees, the third angle is going to be bigger. So
And,
B be going down.
and the third angle is going to be what?
130.
The third angle will be 130 as well, yes.
You don't want to go straight down anyway. So we're going to have
Yeah, we could do that. We could have B go straight down and then make the other ones go from there. But it's arbitrary again, right? What is down and what is up, what is left and what is right here? It's based on our axis. So that works. I like what Chris said. You hear what Chris said? He said, you know what? This is 130 also, just because the sum of these three angles has to be 360. It's a circle, right? So that's got to be 130 in the diagram. And then Chris is saying, like, let's just make this the negative y-axis going down so that the other ones are symmetric. I would agree with Chris. That makes the problem a lot easier, actually. Okay, so we don't have to worry, or we can simplify our parts C and A with the same angle. So let's call this the negative y-axis. Let's call this the positive y-axis. This is the positive x-axis. And this is the negative x-axis. Okay, all stemming from the center where this object was to start. Good idea, Chris. I think that's smart. Along the y-axis would be. All right, so obviously object B only moves in the y direction, which is great. You don't have to worry about its x component. But then we have the x components of A and C, and what are they going to do to each other, those x components? The x components of A and C must cancel out, balance, right? Because they're the only thing acting in the x direction. Again, B is not acting in the x direction, so the x components of A and C can allow us to determine the other part very quickly. So we could say in this problem here, all right, well, let's look at our angles and let's make sense of them. Now, this angle here is going to be 40 degrees. Does everybody agree with that? Because it was 130 minus the 90. This angle here is going to be 40 degrees. And that's logical because 40, 40, and 100 add up to 180 on the top half. So we know that the 40 was right. And why am I specifying the 40? Because it's with the x-axis. And when it's with the x-axis, the x component is cosine, the y component is sine. It becomes very easy to look at it that way when the angle is given with the x-axis. So I'm going to use that 40-degree angle. So the x components, let me move this stuff down if I can. I can't cross that out, of course, because this program sometimes glitches. So I'm going to scroll down a little bit. I'm going to do the x below because I ran out of room there. So let's start with the y now. I'm going to have the y first. So the particle that's B, mass B, goes directly in the y direction. And we know that momentum is m times v. So you've got the mass of object B times the velocity of object B at the end. And that's going to be in the negative direction. So I'm going to put a negative sign out here. Then I've got plus the mass of object A times the velocity of object A, but we want its y component, so multiply by the sine of 40 degrees. And then the mass of object B, C at the end. We have B already. The velocity of object C afterward times its y component, which is sine 40 also. And that equals 0. So B goes straight down, MA, mass of object A, goes up and to the right, so we have a component of it, and object C goes up and to the right or left, either one, so it's upward either way, so it's another sine component. Notice that both, in this case, A and C are positive because they are going up. B is going down according to our tilted axes. Now, we have numbers for things, so let's figure out what those numbers are. I think we're going to run into a problem with the y direction. We're going to have too many unknowns, so we're probably going to have to go to the x direction to get a second equation so that we can use a system of equations. Spence?
Well, in this case, aren't VFA and VFC equal?
Only if their masses are equal. The masses are not given to be equal. And actually, you know, it's a good point that Spence just mentioned. We should list the mass of object A, right? If B and C are 0.3 and 0.2 of the original mass, how much is left for mass of object A? What proportion?
0.5.
0.5 of the original mass. So let's look at this, right? If these two together combine to be half of the original mass, that means that the mass of object A must be the other half of the original mass. Now, let's use common sense here. If the original mass is the same in the beginning as it is afterward, because there are proportions of it, do I really need to put that capital M in all of these parts here? Like, do I have to make this here 0.2 M, 0.5 M, 0.3 M?
No.
What's going to happen if M's in all equations?
It's
Well,
gonna cancel
it's
out.
going to cancel anyway, right? If big M is in all three terms of this equation, big M will cancel. So as a result, I don't have to worry about big M being in the equation because it's going to drop off. So let's just call our masses 0.3, 0.2, and 0.5 in the equation. Again, it doesn't make a difference, it's 6 and 1/2 dozen, but just think about that stuff to make life easier. So that's 0.2. We don't know the velocity of object B afterward. That's the unknown there. Object A is 0.5. Really? My pencil just died, I think, guys. Give me 1 second. Object A, keep writing, please. Object A is 0.5. The velocity of object A afterward is unknown, so that's another unknown, VFA in the middle there. So this is 0.5, VFA sine 40. The mass of object C is 0.3. VFC is 5, and then times sine 40. So let's fill in all of our unknowns there. I should have some energy now. VFA is unknown. Sine 40 is a value. MC is 0.3. VFC is given as 5 in the problem, and it's still sine 40 equals 0 there. So again, notice what happens here. The y direction has two unknowns. So for these problems, I'm guaranteeing you, on a two-dimensional conservation of momentum problem, you will most likely, almost surely have two unknowns. Why again will you most likely have two unknowns in this problem on a test? What do you think? Why will there most likely be two unknowns and not one?
X and Y.
Because you have two directions to look at. You have the x direction and you have the y direction. If you looked at a problem with the z direction as well, you could have three unknowns in that problem and solve for the three variables. It's pretty much a system, and you guys know that. The number of unknowns equals the number of equations that you have. So we must have a second equation. Let's move to the x direction. In the x direction, part B does not matter. Remember, the mass of object B does not matter in the x direction. So I could write MB VFB times the cosine of 90 degrees. But what's the cosine of 90 degrees?
Wait,
0. So this whole thing becomes 0. Again, we don't even need to list the momentum of object B because it's only moving in the negative y direction. I'm putting it there just to make a point. But if we do list it, the angle is 90 degrees with respect to the x-axis between object B and the x-axis, so cosine of 90 is going to be 0. Then after that, we have the mass of object A, and this is going to be a negative actually, right? Object A, because it's moving to the left. I'll point to it up here in the diagram. Here's object A at the top. It's going to be moving up and to the left, so its x component has to be negative, times the velocity of object A afterward, times the cosine of 40. And then object C is moving to the right, so that's a positive. And there's my equation. And then because I'm given this information, or I'm given enough of this information, I can now plug into the x direction, negative mass of object A, times the velocity of object A, which is unknown, times the cosine of 40, plus mass of object C, times its velocity, speed really, times the cosine of 40, and that equals 0. So in the x direction, we solve for VFA. What do we then do once we get VFA? Once we get VFA, what do we do? Plug it in, right here, for VFA, and then get VFB. I'm not going to go through algebra. You guys are way more than smart enough to do this yourself. Okay, I'm not going to go through the algebra involved here. So you are. VFA is the first thing to solve for in the x direction, plug into the y, and get VFB. It's just a number crunching at this point. Chip.
Should your value
Should your value for the VFA in the y direction be negative? No. Because objects A and C are doing this, right?
Right.
So they're both going in the upward direction when you consider it to the y. So that's why these are both positives. B is going down in the y direction, which is why it is negative. So it's still a vector quantity. Remember, vector quantity for this. Okay? Good? Any other questions on this one? Does the setup make sense? The logic? I know that I did conservation of momentum a lot last year, but only in one dimension. We didn't do two-dimensional. So I want you guys to see, when it's a two-dimensional problem, it's treated the same way. It's just that you have the x and the y direction. That's all you have. The x and the y direction. All right. With that said, I want to move in. That was an example from 9.5, just conservation of momentum. I want to move to an example from 9.6, one of my favorite ones of the year. This is on page 236. We're going to look at what's called the ballistic pendulum. The ballistic pendulum. Okay, so this is page 236. That last one was on page, in case you're checking back. Oh, what was it on? It was on page, thank you, 232. Thanks, Em. So 236, here's what it says. Here's an example of a common technique in physics, and it is common actually. And actually I should say it was common. It is no longer common as a technique. The ballistic pendulum was a device that was used to measure the velocity of a projectile. Before we had what? What do we use now? Photo gate, motion sensors. In real life, what do policemen use? Radar guns, or baseball players should say? Radar guns, right? So a radar gun does exactly that. It takes the actual time it takes for this object to bounce back, it knows how far it traveled, it estimates the velocity there. Well, photos use the same thing with the timing mechanism. But before electronics were around, you couldn't do anything, right? All of what we just said involves electronics. So, without electronics, how do you measure the velocity of the projectile? So the question becomes, can we use some sort of a method of conservation to allow us to find that projectile's velocity? And the answer is yes, we can, obviously, because we're going to do it here. So the setup was as follows. We took a pendulum, okay? We took a pendulum like this, and an object was fired, say a bullet. The bullet would hit the pendulum. The pendulum was usually made out of wood. The bullet would embed itself into the pendulum. The pendulum would rise up to a certain height. The angle was measured. Based on the angle measurement, the object would fall back to where it is, and the angle measurement would indicate to us how much energy and potential it had, which could allow us to figure out how much kinetic energy the system had at the bottom. With the kinetic energy at the bottom, we can determine the velocity of the object when it hit the system. If we know the velocity of the system when the bullet hits, we can find the velocity of the bullet it started with. It's like a three-part problem. Would there be Q loss? The assumption here is that the Q loss is negligible, which it's not. So you know that the muzzle velocity will be at least greater than the value that we determined.
We don't play like the margin of error would be, and also the margin of error would vary depending on what's being fired, right?
It could matter on that, it could matter on the materials. There's a lot of parameters that can come into play, so it's a bit unfortunate. I'm really pissed that I was late today, by the way, because I want to be early actually, so I can set this up for you, but it'll take me 2 seconds to set it up. Okay. So this is a ballistic pendulum. Let's see how nicely it works today.
There's a lot of motion, like projectile launchers and this sort of thing.
There are a lot of projectile launchers.
Yeah, like a lot of things that can be used as like guns.
So take a look. So take a look. Well, it's physics though, so it's.
As they should be.
So take a look here. You'll see there's 3 notches. Each notch gives it a different amount of spring energy stored. There's a spring in here. So you well, look on the highest one, sure. So we can vary that value. I was gonna say, but we just jump to the highest one, I guess. For the sake of time, it makes sense anyway.
Let's go.
You project out here. Okay. There's a plunger inside of here. That plunger will push the projectile. That will hit this object, and then this will be recorded. So take a look. If it hits it, it moves up. It'll record exactly the angle you want. Hey, this is way more. This is much nicer than what I have. Obviously. But again, it was like an object coming out of a muscle. Okay. 3, 2, 1. What 11? Huh? 11 degrees. Okay. So 11 degrees is our angle of measurement in that case. Now, this. Yeah, that was really quite a left hand, huh?
That was gonna go like so far up.
Yeah, so was I, to be honest with you.
Wait, what's the lowest ending?
Is it supposed to always go that far? It seems like the
Yeah.
angle that's recording is so much higher.
It's possible I'm supposed to put this, I was going to push it back even further with a plunger, but it's in there, it's as far as it can go in. Now, the mass of the second part matters a lot, obviously. This mass is heavier, like the wooden block is heavier, it's not going to rise up very much. If the mass or velocity of the first one is larger, it will cause it to rise up even further. Let's try one time. 3, 2, 1.
Oh, wow.
That was a little bit better. Didn't
Yeah, but not only is it energy loss, wouldn't there also be like physical mass loss? In the case of the bullet in the wood.
It's a great question. The idea would be that the bullet embedded itself into the wood. So there wouldn't be mass loss if there was no like, shrapnel coming out. And they would specifically use material that the bullet would not go through. Because then it wouldn't make sense because it would stay in it and no mass loss in the back. Show them one more time. 1, 2, 1. Interesting. So one of them easily grabbed in while the other one doesn't. I wonder if it's a magnetism thing. This is the one that did lock in the first time. The second one's not locking in.
Yeah, it's
That was
magnet.
weak. Okay. So it was like 11 degrees. Anyway, the concept I want you guys to get here is that the object is fired from here. It hits the pendulum. The pendulum is at an angle of 0 degrees to start. The object travels like this. It embeds itself inside of here. And then the object, or the giant pendulum, with the object inside of it, swings up to an angle that can be measured. And this is the problem itself. So let's take a look at the data that's given in the problem in the text. We're told the following. The version of this pendulum consists of a large block of wood with a mass of 5.4 kilograms. A bullet of mass 9.5 grams is fired. So big M and little m they use. It comes quickly to rest. The block and bullet swings upward. Their center of mass rises a vertical distance of 6.3 centimeters. Oh, so they made it easier for us. I'm going to make it harder on us. That's too easy, okay? They made it so that they give you the vertical center of mass height difference, which what they're saying is like the center of mass from here to here. They were giving you that vertical height differential between these two right here. But if they give you that, it's just too easy. Then you know the delta H, you know the potential energy gain. So instead, I'm going to give us the length of the chord, and I'm going to give us the angle, which makes it a more difficult problem where you would probably see like a part 2 on an AP exam. So let's say the angle, let's use our number from here. Let's say it's 11 degrees. Okay? And let's say the length of the chord is, what is that? About, I don't know, a foot, 30 centimeters. So 30 centimeters works. Okay? All right. So we have the length of the chord. We have the angle of 11 degrees. We have to figure out that differential in height. Right? This differential in height matters a lot right here. We have to figure out what the differential will be. So how can we figure out what that differential will be? Well, here's the thing. My diagram is not drawn nicely to scale. Really, this dotted object should go a little bit higher up like this is what it should look like, okay? I know it's not drawn perfectly to scale. And our chord should only go to here. So let me see if I can erase any parts of this. I can't. Nice. So really, the differential in height, instead of drawing it there, watch where I'm going to draw the differential in height now. Give me a second. Okay? The easier way to draw the differential in height would be here. From the top of the rope to the top of the rope. Now, the center of mass of the system does technically change when the bullet embeds itself, which is why the book gave you the center of mass and told you how far the center of mass rises. Here's the thing though. If the center of mass, or if the bullet embeds itself directly in the center vertically, the center of mass vertically won't change. It will only move in the leftward direction, right? In the leftward direction, because the bullet is definitely more dense than the actual wood. If the bullet were made out of the same material as the wood, it would still cause a slight change in the center of mass, because the wood inside of here would kind of get compressed from the bullet. Does everybody follow what I'm getting at? The bullet embedding, the wood gets compressed, which changes its density, which makes it a non-isotropic material now. So we're going to assume, for the sake of assumptions here, that this object being embedded by the bullet doesn't really vary its center of mass too much, so that we can change the differential height, or we could set the differential height here to be from where the rope is attached to where the rope is attached. So that's the gain in height right there. And that's the gain in height right there. Now, let's say that the length of the chord is 30 centimeters. The degree is 11 degrees. So what we can do is we could figure out what the actual length is there by completing the triangle. So please complete the triangle right here. Make yourself a little right triangle with that dotted blue line. Make yourself a right triangle with the dotted blue line there. We're going to have to figure out, let's see, if that full length is 30, right? If that full length is 30, let's call this H right here. That's the part that it's going to gain in height. Everybody agree with that? See what I'm calling that H? So we know that the original position of this object was at a height of, let's say, 0, and we have to see how much it gains. We have to figure out what that H is. So let's see if we can figure that out with a little bit of trig. So we would need to figure out...
So we know 30 is the hypotenuse for the second.
This guy is 30 centimeters, so it's the same chord physically. So we can figure out if this is 30, right, and this is 11,
You can figure out the y.
we can figure out from here to here only. And then subtract that from 30 to get what's left here. Think about this problem for a second. We know the hypotenuse is 30 because this chord is 30, so whether the chord is from there to there or from there to there, it's 30. So given the hypotenuse of 30, we could find this component of the triangle, which is from here to here, and then subtract that from 30 to get h. So how are we going to figure out that component of the triangle? It's the cosine for this one because it's the adjacent side. Again, let's call this right here, let's call this H star. Okay, the height above the blue dotted line, the height below we'll call H. So let's figure out H star and subtract H star from 30 to get H. So we'll say the cosine of 11 degrees equals adjacent, which is H star, over hypotenuse, which is 30 centimeters. Therefore, H star is equal to 30 times the cosine of 11. Can somebody give me a number for that real quick?
29.4.
Okay, if that's H star, subtract that from 30, so we get 0.55 for H. So there's the change in height, 0.55 centimeters. Again, this is the way it's traditionally given. I guess the book gave you with the center of mass, so you didn't have to consider the center of mass changing, and I understand that idea. But you're going to see really where the angle is measured itself, the angle. All right, so the height of 0.55 centimeters. What does that tell us again? Give me one sec, Chris.
The potential energy, which is 29.1.
Yeah, that gives us the potential energy when, though? At the highest point, when the object is not doing what?
Moving.
When it's not moving. So let's talk about our types of energy. Here, it's all potential energy. Here, it's all kinetic energy. Right? At the bottom of the path, it has only kinetic energy because it gains velocity from the bullet hitting it. But it doesn't have any height at the bottom of the path, so it's all kinetic at the bottom and all potential when the pendulum gets to the top of its arc or swing. So as Spence said, let's call this ground level. Let's call that ground level so that all the energy at the top is all potential and at the bottom there's no potential. So we call that ground level in our problem. We could say that the potential energy at the end of this problem is equal to the mass of the system, which is the block, and the bullet, times G times H. The mass of the block is 5.4. The mass of the bullet, be careful, is in grams. Make sure to convert that. 0.0095 times 9.8. And my height is in centimeters. We got to convert that also. What is that going to be? 2 more zeros? 0.0055. .0055, yeah?
Yeah, it's 0.29 for
What do we get? We get .29 as a number?
the 0.29. Yeah, 0.2915.
And I'm going to keep those extra decimals for now, just because of the fact that I'm going to use this number in a little bit. So that's the amount of energy that this two-mass system gains as the pendulum swings up to its highest point in the path. This amount of energy, now again, I know it's not the case here, but we have to assume that it's an elastic collision still. We have to make that assumption that it's not inelastic because we can't figure out the change in kinetic energy as a result of these two things hitting with the information given. So we have to say that the kinetic energy at the bottom of the path is equal to that value. Okay, that's the statement we have to make. The kinetic energy, when the bullet embeds itself into the block, has to be equal to the amount of potential energy at the top there. Now, what else could we do? Where did all the energy start? In the bullet. So what else could we do instead of worrying about the block at the bottom instead? Worry about the kinetic energy of the bullet in the beginning. If we have enough information, we could set the kinetic energy of the bullet in the beginning equal to the potential energy of the block and the bullet at the end, if we have enough information for it. So let's think about this. We have the total energy at the end. In this problem, are we given? Yeah, we're given the mass of the bullet. So yeah, we could do that as well. But the idea that this problem wants you to work with is they want you to look at the problem and say to yourself, well, let's look at the idea of conservation of momentum because there's a collision. And if we want to, we can find the change in kinetic energy here from here to here and then go to the next part, if we don't assume that it's an elastic collision. So let's call this K0 and let's call this UF. Let's call that K0, let's call that UF. So K0 at that point is 1/2 m plus m v of the system squared. And that equals 0.2915. This allows me to solve for the velocity of the system when it is about to impact the actual block. So give me the velocity of the system, which is the velocity at this moment right here. That's what we're solving for right now. We're looking at the velocity right here when this bullet just embeds itself into the block. It gives it velocity to get it moving, and that's this velocity here. And they're combined, so we put big M plus little m. What does that come out to be? Can I get a calculation, please?
0.33.
This is not our answer, but it's an intermediate answer. It's an intermediate answer. We then know, due to conservation of momentum, that the momentum of the bullet initially has to equal the momentum of the bullet in the block when it collides. Exactly. So we have to recognize that the Vs is not the velocity of the bullet, but it's the velocity of the bullet and the block together right when it embeds itself. But we know that the mass of the bullet times its velocity initially is the momentum of the system initially. And that's going to equal the momentum of the system at the end. So now we're considering this the beginning of the problem, and we're calling this the end of the problem for the collision problem in the beginning. This is all about looking at the conservation of momentum in the beginning. This was looking at conservation of energy over here. So that's going to equal the momentum of the block bullet system, which is m plus m times that Vs that we just got a moment ago. So we've got conservation of energy from when the bullet block starts to rise up, but we've got conservation of momentum between when the bullet is fired and when the bullet embeds itself. When it's fired is before. When it embeds itself, it's the after. So we could solve for V0 in this problem. We know everything else. We've got 0.0095 plus 5.4 times the velocity of the system, which was 0.33, all over the mass of the little block, little bullet, 0.095. That'll give us the velocity of the bullet as it it was fired out of the, whatever, rifle, barrel, whatever you want to call it. Muzzle velocity is the phrase. What do you got?
187 meters per second.
Point. So 188. Depending on rounding, you may round it to the proper. So
Yeah.
anyway, point being, look, the muzzle velocity of the bullet extremely high. Then suddenly it hits the block. It slows down dramatically, which causes it only to raise to a height of 0.55 centimeters, which we got from knowing the angle theta and knowing the length of the cord. This is a perfect part 2 problem, combining what? Conservation of momentum and conservation of energy. Okay? Conservation of momentum and energy. Is it elastic or inelastic? Determine. Go.
Inelastic. Realistically, it's elastic.
Realistically, it's inelastic because we know that. Because this type of a collision is. Prove that it's inelastic. Find the energy in the bullet here and compare it to the energy in the block, which would be this number, right?
Well, here it's elastic. Yeah.
So figure out the energy. Do 1/2 mv squared with this, please. Find the energy, the kinetic energy. 1/2 times 0.095 times 188 squared. How much kinetic energy did the bullet have to start in the very beginning of the problem?
167.884 joules.
Look at that energy level. That's how much energy the bullet had. But look how much energy we've got in the block system right here, right? That's the energy the block system has. So it is a very inelastic collision. This number is definitely right, right? I'll just check to verify. Good. You see what I'm getting at here? So although in the beginning I was like, oh, we have to assume it's elastic collision to see that. It's actually not elastic at all. It's inelastic for sure. But we didn't have to actually use the nature of the inelasticity to solve the problem. Instead, the follow-up question, maybe part C would say, prove that this is an inelastic collision. Because every student in physics knows that when two things stick together, it's an inelastic collision. It's only going to be elastic when they hit and bounce off. Or the best example of inelastic is when they actually don't hit. So the carts, I'm going to show you next class because we're going to run out of time. When they try to collide, there's magnets between them, which forces them apart. So the first one almost hits the second one and it just pushes it. It doesn't ever touch. So that's the best example of elastic that we can show in a lab. But the best example of elastic actually are gas particles in a trap container. Those are practically elastic collisions. They're modeled to be completely elastic. And clearly this is inelastic based on the energy of the bullet initially being much greater than the energy in the block at the end or the energy in the block at the bottom. These energies are the same. Remember, we set the potential energy at the end equal to the kinetic energy of the block and the bullet at the bottom, which is far less than the kinetic energy of the bullet to start. Okay?
So for the energy loss here, it would come from the work done
By the embedding of the bullet. Probably a lot of heat, actually. If you've ever done anything like bent a paper clip or rubbed your hand on enough things.
I burnt my finger last year on a catapult project.
Perfect, even better.
Drilling something with a screw.
Using a drill over and over on wood, right? And then you go to take the drill bit out. What happens to the drill bit? It's really hot because the metal drill bit is ripping through wood. Well, this is metal tearing through wood. There's definitely going to be heat generated. What else is generated? What else is generated? Sound. A lot of sound. So a lot of the energy is lost to sound and heat. The heat of embedding it into the bullet, into the block. And the block deforming. Remember, the block itself gets compressed by the bullet embedding itself into it. Next class. Okay, I'm going to give you a quiz. I'm going to tell you that now for sure. Expect a quiz on like 9.3, 9.4. That's an older topic of momentum. Did I give you something on 9.3, 9.4? That's what I did. But I'm going to give you more mathematical and momentum and impulse. Okay? I will assign homework from 9.5 to 9.7. I already put up a multiple choice for it. I'll give you prompts in the textbook to look at next time. We will look at probably one more 9.7, maybe one more 9.7. I also sent you an email. Did you guys see that? Try it out. I'm really curious. It looks really cool. It's called Ed Puzzle. It allows me to have you guys do flip classroom on and answer questions that I've created throughout the video. You can answer, and it tracks whether you watched it or not. So please sign up for that Ed Puzzle account. If you have trouble signing up, come see me, please. I've never done it before, so please let me know if there's any issues. Have a good day, guys.